Hi everyone. Good morning. Thank you for seeing my presentation. My name is Jaskarun. I'm a PhD student in the Robotics Institute at Carnegie Mellon. I will be talking about my paper called System Identification of Safe Controllers Using Inverse Optimization. The goal of this work is to reverse engineer the tasks being performed by individual robots in a multi-robot system by tracking their positions and velocities. This is the outline of this talk. Let us begin with the motivation. Multi-robot systems have been used for many tasks, such as search and rescue, exploration, and coverage. Synthesizing controls for these tasks is a forward problem, and it is relatively well studied. On the other hand, the inverse problem, that is task inference, has not been explored as much in the context of multi-robot systems. Now, observer-based inference has several applications. For example, our observer could be another robot team, and here the question becomes, how can this team learn by imitating an expert team? On the other hand, our observer could be an adversarial team, and here the question becomes how easy it is for the observer to reverse engineer the task being performed by the team being watched. So the research we did in this paper is an attempt to answer these questions. So in this work, we pose prior inverse optimization algorithms in the form of a robotics learning problem to infer task or cost function parameters of optimization-based controllers used in multi-robot systems. We derive novel QP-based reformulations of these algorithms for faster processing of batch data. We analyze failure cases of these algorithms using the persistency of excitation criterion. And finally, we validate these algorithms using simulations and experiments with multiple robots. So let us look at the forward problem of the robots now. So let's see the setup. We have n robots in the system, but let's just focus on one robot, say robot I, to begin with. This robot must find a control ui to finish a task parameterized by theta I while avoiding collisions with every other robot. Now let us assume that there is a nominal reference control ui cap, and we take it as a given that this control guarantees completion of the task parameterized by theta I for robot I. For ensuring safety, a linear constraint on the control has been proposed previously, which guarantees a distance of at least d sub s between every pair of robots. Now, to mediate between the task completion and safety requirements, a quadratic program is developed which computes a control that is closest to the task-based control ui cap and also guarantees safety. So going forward, we will assume that all robots are using this QP as the underlying control synthesis module. So now that we have seen the task-based safe control synthesis algorithm, let us come to the main topic of the paper, that is task inference. The task inference problem requires us to develop a batch algorithm to infer the task parameter theta I by using the positions and velocities of each robot in the system measured over some time. So suppose there are 4 robots, each trying to go to a goal location. Then the task inference problem can be, for example, to find out the goal location, in this case the goal of the yellow robot, by just tracking the positions and velocities of the yellow robot and the remaining robots in the system. So let's look at the inference algorithms that we have developed in this work. Let me first present the general approach that is common to all the inference algorithms. We first collect signal response pairs for the robot whose task we want to infer. The signals are the positions of that particular ego robot and the remaining robots, and the responses are the safe controls of velocities that the ego robot computes in response to its position x ego and the positions of other robots, that is x others. Then we use this data to pose an empirical risk minimization problem by leveraging the optimality conditions of the forward problem that all the robots are solving. Finally, we solve this empirical risk minimization problem for the parameter theta ego and some other variables that we don't care about, subject to the optimality conditions of the forward problem. So to begin with, let's look at the predictability loss minimization problem. So the idea here is as follows. Remember that we have the true underlying system in the ego robot that generates the controls UI star in response to the positions x of the ego robot and other robots, and it depends on the parameter theta star, which is this, which the observer wishes to infer. Now, the observer can watch and measure these controls at every time step, and we call these controls U star measure of t. Now, the observer makes a copy of the true system, which is this here, since the observer has all information except for theta star. Theta star is what the observer wishes to infer. So theta star is replaced by theta cap here. Now, for the same position x, which was going into the original system, the observer produces a control U star predicted, which is U star pred. Now, if theta cap was the same as theta star, then U star predicted should be equals to U star measure. The norm of the difference between the observed measured control and the predicted control is called the predictability loss. And the idea behind the predictability loss minimization algorithm is that by minimizing this difference of these two controls, the error between the theta cap and theta star will also get minimized, and that's how we will infer theta star. So as I said, by minimizing the predictability loss, we will indirectly end up minimizing the error between the estimate theta cap and the true theta star that we want to infer. This can be posed mathematically as such. The objective is to search for the predicted controls and parameter theta cap, which minimize the total predictability loss that is summed over all time steps. The constraint requires that the predicted controls U cap star be a solution to the copy of the forward problem that the ego robot is solving that we saw in the previous slide. Now, as you can see, this constraint in the inner problem involves an optimization problem in itself. And therefore, this makes the overall problem a bi-level optimization problem, which is computationally difficult to solve. So in prior work, we convert this, using ideas from prior work, we convert this bi-level problem to a single level problem by using the necessary conditions of optimality. This comes at the cost of increasing the number of decision variables, since now we have to learn Lagrange multipliers at every time step as well, in addition to the predicted controls and the parameter theta cap that we were doing in the bi-level problem. Nevertheless, this single level problem now is still non-convex, and therefore it requires the use of general NLP solvers such as fmincon and MATLAB, which makes this approach slightly slow. So now we'll look at another algorithm in which we have a convex approach to solve the inference problem. So that is the KKT loss minimization algorithm. Here, we leverage the KKT conditions of the forward problem to pose a loss function for learning theta. So remember, this was the forward problem in which the ego robot is trying to find a control closest to the reference control that depends on theta, subject to the safety constraints, and the goal is to learn theta. The KKT conditions of this forward problem are stationarity, primal feasibility, dual feasibility, and complementary slackness. So using these conditions, we now search for Lagrange multipliers at all time steps and the parameter theta that minimize the sum of the stationarity loss and the complementary slackness loss over all time steps. Additionally, we constrain the Lagrange multipliers to be non-negative to respect the dual feasibility of the forward problem. So this is the KKT loss minimization problem. Now recall that the nominal control U cap is affine in theta, and this makes the loss function quadratic in both theta as well as in the Lagrange multipliers mu. Moreover, the constraints here in this problem are linear in the Lagrange multipliers. Therefore, these observations allow us to pose this KKT loss minimization problem in the form of a convex QP, because the cost function is is quadratic in both theta as well as Lagrange multipliers, and the constraints are linear. So this is the original problem, and this becomes a QP in nu, where nu is a vector containing all the Lagrange multipliers and the parameters theta that we want to learn. This can be solved efficiently using state-of-the-art QP solvers. Here Q, F, capital F, and G are some matrices and vectors that depend on the data of the system that we have. You can refer to the paper for more details on how to compute these. Finally, let's look at the suboptimality loss minimization algorithm. This algorithm is based on minimizing the suboptimality loss. This approach looks at the forward problem as a variational inequality problem and tries to minimize the suboptimality of the observed decisions. The approach for inference in this case can also be formulated as a QP, and it looks simpler, yet to arrive at this approach there is a lot of moving parts involved. So I will defer the rest of the details to pose this problem to the paper, because this method is rather involved and too time-consuming for the presentation. Now let's look at some simulation results. So we have a go-to-goal task requiring each robot to stabilize to a goal position and remain collision-free with other robots. Here is a sample video that shows the experiment. The reference control in this case is simply a proportional controller for stabilizing to a goal. And the unknown parameters theta I for each robot that we want to infer are the proportional controller gain KPI and the location of the goal of each robot. We conducted several simulations to infer the goal location and the gain to validate these algorithms using the data that we gathered in the simulations. And these tables indeed show that the gain and the goal estimation errors are very close to zero for all robots for all the three algorithms. Next, we wanted to test these algorithms under some corner cases where we thought that the inference would not work. So to convey the idea, I will only consider one robot moving among static obstacles, but it is also applicable to the multi-robot case. So in our previous work, we showed that if the observer is watching the ego robot during a time when the ego robot has active interactions with two or more than two obstacles, then during this window, inference will not succeed. And this actually follows from the persistency of excitation criterion, and more details can be found in this paper that we got accepted in Multi-Robot Systems Conference. So for the first and second case here, inference will be successful because the ego robot has active interactions with either zero obstacle or one obstacle. But for the third case, during the time in which the ego robot has active interactions with obstacle number 4 and 6, inference will not be successful. And so for these corner cases, we do indeed confirm this result for the inverse optimization based algorithms as well. This table shows the goal estimation errors with increasing number of active obstacles for the three inverse optimization algorithms, as well as an unscented Kalman filter and an adaptive observer that we used as baselines. The last row here corresponds to the case where there are two active obstacles, and as these errors show, they're very large compared to the errors for the case of 0 and 1 active obstacle, which confirms our theory that goal inference becomes inaccurate as the number of active obstacles increases because of the violation of persistency of excitation criteria. Then let's look at some validation on real robots as well. So to test these algorithms in the presence of perception noise as well as hardware noise, we conducted several experiments with 3 Kibera robots in our lab. So these robots are implementing goal stabilization with collision avoidance maneuvers, for which we showed the theory before. And just like before, the inference algorithm has to infer the location of the goal. So we used YCon for tracking the positions of the robots. So there is naturally some perception noise in the system. So this table shows the absolute goal inference errors in meters, and as can be noted, the mean error for all the algorithms is between 1 centimeters to 5 centimeters, which is quite small. Therefore, our algorithm does work in the presence of noise as well. So let's conclude the talk now. So in summary, we used prior inverse optimization based inference algorithms and reformatted these algorithms to perform learning of task parameters in a multi-robot system. We developed novel QP-based reformulation of the KKT loss minimization algorithm and the suboptimality loss minimization algorithm for faster inference. We also analyzed some failure cases of these algorithms using the persistence effect citation criterion. And our results demonstrate accurate reconstruction of goals and gains in both simulations with no noise, as well as experiments where there is some noise due to hardware. And with that, I'd like to thank you for listening to my presentation, and please feel free to reach out to me for any questions. Thank you.